Hello, in today's video, I'm going to be covering section T of our catalog, thermostats. If you have enjoyed this series of training on our catalog and would like a similar training or more training on our product, go to kimray.com/training and you can set up a time for us to come to you to your office or for you to come to a Kimray store location. But if you need any kind of Kimray training, we'd love to provide that for you. All right, let's go ahead and get started with section T of our catalog. So thermostats control temperature of different processes. There's a couple of different options with the models within section T, but they control anywhere from -30 all the way up to 750 degrees Fahrenheit. That is their temperature operating range. I would say majority of the processes in oil and gas are not going to be outside of that range. You've got a T12, and T12 is just its thermostat, and then the 12 is the length of the probe. We did used to offer not only a T12, but a T16, a T24. We no longer offer those longer sizes, just the T12. But we'll dive in. Here you can see a burner management system. When you have all of these components working together, they're connected in series. If the pilot guard's not sensing a pilot flame, it will not let supply gas through to the rest of the components. If there is a pilot flame present, it'll let supply gas through to the high temperature shutdown. If you're below that set point, then that will let gas through to the normally operating T12, which will then be controlling a burner valve. So if any one of those components in that series has an upset condition, it closes down the entire burner system, so that way things don't get overheated or damage is not caused to the equipment. So we have two burner valves in this example. We have one that's the normally operating burner valve. So the T12 will be communicating with that, opening and closing it to control the temperature inside of the vessel. Then we also have a secondary safety shutdown valve that will be communicating with the high temperature shutdown valve. So if we ever get above our high temperature set point, most likely that's an indication that our burner valve has failed in some way. It's staying open when it shouldn't, and so it's continuing to feed the burner with fuel, increasing that temperature up to that high temperature set point. And so we have a secondary valve that will shut down. It's downstream of the burner valve, as you can see in this example. The different pieces of equipment that our thermostat is typically used on. Here you can see it's being used on a heater treater, but any heated piece of equipment can use the thermostat to control the temperature inside of that vessel. So we've got heater treaters, line heaters, in any heated vessel outside of maintaining and controlling the temperature of a fluid bath or a liquid. There are a few applications where you can use this to control and monitor gas temperature. I've seen a few applications where people will be monitoring the discharge temperature on a gas compressor. If the temperature is getting too hot, it could open up a bypass valve to send the hot gas to additional cooling. Maybe it's opening up the louvers on the cooler more if it needs to be cooled more, or shutting them if the gas is getting too cold. So there are a few different applications, not just on heated vessels, but the probe itself can be in gas or liquid. It's not only to monitor liquid temperatures, though typically it is used in liquid applications. Our temperature controllers can be direct acting or indirect acting. They can be switched from one to the other without adding any additional parts. You just have to put the supply and the vent in different spots. You have to switch the two. So direct acting temperature controllers, when you have a rise in temperature above your set point, the controller will have a pneumatic output. So it's a direct action. Above set point, you're going to have high output, or you're going to have output from the valve, or the temperature controller, rather. In indirect mode, if you are above your temperature set point, the controller will be venting its output. And then if you go below your temperature set point, the controller will have a pneumatic output. So it's kind of an opposite reaction from the process temperature and what's happening with the process temperature. Most typically, the burner valves that the temperature controllers are going to be operating are going to be fail-closed valves. And so in that application, in that scenario, you want an indirect acting temperature controller. So when you have a rise in temperature above your set point, that means you want to close that burner valve. So if it's a fail-closed valve, or pressure open is another way you could say that. When you have a rise above your set point, that controller will be venting that signal that's holding that burner valve open. And so that will cause the burner valve to go to its failure position, which is closed, closing off the path for fuel to get to the burner. So that will start cooling the temperature back down. In other applications where you have, high temperature shutdowns and things like that, that is most typically going to be an indirect acting as well. Again, depending on the failure position of the valve it's working with. So just keep that in mind. But any switch between direct and indirect acting, it's just about where the supply is coming into the controller. So if we look at this example right here, the purple is the supply. So on indirect acting, the supply is coming into the connection closest to the vessel. The output remains the same whether you are in indirect acting or direct acting mode, but the vent on an indirect acting temperature controller will be the connection furthest away from the vessel. Now, if you look down below, we've got a direct acting temperature controller, and all that has happened is the supply and vent have changed places. So now the connection closest to the vessel is the vent, and the connection furthest away from the vessel is where you bring your supply into. So if the temperature controller is operating a high pressure control valve, so any valve found in section CV of our catalog, the actuator of that valve is completely separated from the process flow. In those scenarios, you can use compressed air for the pneumatic signal and supply for the temperature controller. You want to be careful that you're not using compressed air with any controller, any low pressure burner valve that's found in section B of our catalog. The reason for that is because there is a single diaphragm separating the pneumatic supply coming from the temperature controller and the process flow. So if you were to have a failure of that diaphragm, there's a potential, if you were using compressed air, that you'd have fuel and air mix. But if you're using a high pressure control valve, typically a 1-inch control valve is what people use in this application, you can use compressed air because if there were a failure of the actuator diaphragm in that valve, that pneumatic signal is just venting to atmosphere, and there's no possibility of it mixing with your gas supply. With the use of the T12 as well as the high temperature shutdown manual reset pilots, you can use those with a separable socket. The reason why you would want to use this is that it allows you to remove the T12 from service without having to depressurize or blow down your vessel. It is a pressure containing device, and so you would install the Thermowell into your vessel first, and then the T12 can be installed into the Thermowell. You want to fill the Thermowell with some kind of high temperature grease, so that way the temperature of the process can be transmitted to the probe of the T12 efficiently. But with that, you can remove the T12 without having to depressurize your vessel. So it makes repair a lot easier and faster and more efficient. I want to talk through a few key components of the T12. There's a few parts to replace. We actually have a video on temperature controller repair, and we'll link to that below this video. The areas of concern for the temperature controller is the pilot plug. So when you are supplying this either with natural gas or compressed air, you want to make sure that it's clean and dry. And you also want to make sure that you are operating within the temperature range for that specific temperature controller. So there we have two options for that. We have a T12 and then we have an HT12. So the T12 can operate from negative 30 degrees all the way up to 400 degrees. The HT12 can operate from negative 30 degrees up to 750 degrees Fahrenheit. As I mentioned before, the HT12 is normally used for high temperature shutdown applications. It's paired with a pilot, a manual reset pilot. So the high temp shutdown that I was speaking about it's our part number HAM or HAM, but it's an indirect high temperature shutdown. So as you can see here, it'll be paired with a manual reset pilot. So let's say you wanted to operate a reboiler on a D-high system at 390 degrees. The high temp shutdown would be set somewhere above that. So let's just say like 405 degrees. So 405 degrees is its set point, the indirect shutdown set point. So if it got above that for whatever reason, it got too hot, there was a failure of a valve or something happened to cause that temperature to rise up to that set point of 405 degrees, the pneumatic output of this high temp shutdown would actuate the manual reset pilot, which would close off supply going to the rest of the system. The manual reset pilot forces somebody to go out there and manually reset it. There's a switch on the side of it. And so in a manual burner management system where you don't have any kind of automation, you might realize, oh man, my temperature is going down once something in that process happens to notify you. Whether that's, hey, I'm not drying out my gas enough, or if you're going by and visually checking it, you can see that the switch on the side of the manual reset pilot is actuated. That would be an indication that something has gone wrong. Obviously, you want to look into what caused that upset scenario and make sure that you're fixing what has broken or what has failed before you turn things back on. But it's just a safety device to shut everything down until you can fix it. I mentioned before the pilot guard. The pilot guard is just there to monitor the pilot flame to make sure it's present. It's really similar to like what your hot water heater has at your house. If it's a gas heated hot water heater, you're going to have a thermocouple that is making sure that there's a pilot flame present. The pilot guard is doing the exact same thing. The probe will be directly in the pilot flame, monitoring that, and it will make sure that that's present before it lets supply gas through to the rest of the system. So if pilot flame ever got blown out or is not present, there's no way for that burner system to come on, because if there's no pilot flame there and you open up a burner valve, you're going to be spraying natural gas into the burner, but nothing will be igniting. And so the pilot guard, again, just another step in that process to get to heating your vessel. All right, so I want to cover the operation of the T12, how it operates and functions. So the stainless steel sleeve expands and contracts at a different rate than the low expansion alloy rod. So as temperature increases, the stainless steel jacket will expand and will pull the low expansion alloy rod as well as the diaphragm assembly closer into the vessel. That causes supply to be cut off and the path to vent to open. That would be an indirect acting mode. Now, when things cool off, you'll have a contraction of the sensing element, which would then push the low expansion alloy rod and the diaphragm assembly further out away from the vessel, which would cause supply to go to output, opening up your burner valve to then increase temperature. It's important that the low expansion alloy rod does not come into contact with the outer shell. And that's something that I'll move into talking about troubleshooting. It's important when you're installing the T12s as well as just handling them that you don't carry it by the probe. We want that to remain straight and true. If it gets bent, that can cause the low expansion alloy to come into contact with the outside of the probe, which could cause issues with it expanding and contracting at different rates. So you want to make sure that the probe is straight, you're not handling it by the probe, you're carrying it in a way that will protect that. That's one of the troubleshooting tips I would give. If you're experiencing erratic temperature changes, a bent probe would be one of the main causes of that. Also, the probe not being fully immersed in the liquid that you're trying to control the temperature of. So you want to make sure that it's completely covered with liquid. I've had some questions about using the temperature controller in an outside bridle or in a weld neck, or where there's limited fluid around the sensing element of the T12. Ideal best practice, the temperature sensing element is inside of the vessel, surrounded by a large volume of that liquid. That's not always the case, but the more volume of fluid or liquid that you can have around that temperature sensing element, the more accurate the T12 is going to be with controlling that temperature. If you're having issues with the T12 continuously venting, a few things to keep in mind. You might have wet or dirty supply gas. So just make sure that you're cleaning that up as best you can before it gets sent to the T12. There could be a hole in the diaphragm of the T12 that would cause continuous venting. So just make sure that you're operating in a way, best practices, you can repair these. If the diaphragm is damaged, you will need to replace the diaphragm. Another potential cause for continuous venting would be a weak spring. There is a spring that's on the pilot plug. It could be weak, sometimes even just stretching that out a little bit or replacing it completely with a repair kit should fix that problem. Thanks for spending a little bit of your time with me today. If you found this information helpful, or maybe if you have other troubleshooting tips or weird applications that you've seen our T12 used in, comment below. We'd love to hear from you and interact with you. If you would also like more information on the T12, we have lots of resources on that. We've recently done a podcast on it. We have other repair videos and information on our website about the T12, so I would encourage you to check that out. And thanks for watching.